Welcome to this video in which we will be talking about how to code the cubic spline interpolation, so that by the end of this video you will have the foundations ready to actually tackle coding this method in MATLAB. So here's a summary slide of cubic splines that we developed in a prior video. We have 4 equations per interval, where for the first interval we have the condition that the cubic spline goes through the endpoint data points, and then the condition that it is a natural cubic spline. Those are the third and fourth equation on this slide. And then we have 4 equations for each interval from the second to the very last interval, n-1. So in this video I will touch upon how to code 2 of these equations, and then we will tackle how to code the other ones in an upcoming recitation. So we will focus on these 2 equations, that the cubic spline has to go through the left endpoint of the interval, and that, as an example, the second derivative at the knot, at the left point of the interval, has to be equal to the value of the second derivative at the neighboring interval. So let's start with the first equation that's shown here as an example. yi is equal to ai xi cubed plus bi xi squared plus ci xi plus di. And I've summarized here on top what we know about these cubic splines, that we have 4 equations per interval, so that if we have an interval I, the associated row numbers in the matrix from these 4 equations are just I minus 1 times 4 plus 1 plus 2 plus 3 and plus 4. So these 4 equations appear one after the other in the rows of the matrix. And once we've defined a particular sorting for the unknown quantities a1, b1, c1, d1, then a2, b2, c2, d2, and so on through all these subintervals, we know what the column numbers in the matrix are for each one of these a, b, c, and d's for the interval I, because that's just the entry number in the vector z. And that would be for interval I, the ai would be in column number I minus 1 times 4 plus 1, the bi plus 2, the ci plus 3, and the di plus 4. They come one after the other for the interval I in the vector, and therefore also in the columns of the matrix. So let's look at this first equation for interval I. It's the first equation for interval I, so that will go into the row number I minus 1 times 4 plus 1. Now, what is the coefficient that has to go into the matrix that multiplies the unknown a sub I? Well, we just look in the equation. The thing that multiplies a sub I is the data value xi cubed. Okay, so that multiplies ai, so that has to be the entry into the matrix in row number I minus 1 times 4 plus 1. But what is the column number of this ai? Well, we defined the column numbers for ai before. That's I minus 1 times 4 plus 1. Okay, so that means that for the matrix A, my row number is 4 times I minus 1 plus 1. That's the first index, right, that you write into a subindex form for a matrix. That tells you the row number. The second index is the column number. The column number we found for ai is I minus 1 times 4 plus 1 as well. So that entry into the matrix has to be the given value xi cubed. Good. Let's move on to the next entry in this row. That's the one for bi. So what's the coefficient that multiplies bi? If we look at the equation, that's xi squared. In what column does this xi squared go in the matrix? Well, the column that's associated with bi, which is I minus 1 times 4 plus 2. Okay, so therefore, in the matrix A, the row number is still, because we're still in the same equation, it's still 4i minus 1 plus 1. And the column number is now 4 times I minus 1 plus 2. And that entry has to be xi squared. Okay, on to the next quantity, which is ci. What's the coefficient multiplying ci that goes into the matrix? Well, ci gets multiplied by x sub I. That's the coefficient. What's the column number for C sub I? Well, it is I minus 1 times 4 plus 3. Good. So therefore, the entry into the matrix A, still the same row number for I minus 1 plus 1. But the column number is now the one associated with Ci. That's I minus 1 times 4 plus 3. And that entry has to be this Xi. And then finally, we have Di in the equation. So what's the coefficient that multiplies Di? Well, it's kind of hidden, right? It's just 1, right? There's 1 times Di in this equation. The column number still remains I minus 1 times 4 plus 3. And so the column number is, of course, I minus 1 times 4 plus 4, because we're talking about Di after all. The row number remained the same. That's still the same equation. So I minus 1 times 4 plus 1. And the column number for Di is I minus 1 times 4 plus 4. And that entry has to be equal to 1 in the matrix. Okay, so now we just need to set the right-hand side for this equation. So what is the right-hand side? And I call it the right-hand side G. Well, the right-hand side is just the value of y sub I. That's a given data point value. Okay. So I set G in the right entry, so the right row number, I minus 1 times 4 plus 1 is equal to the y sub I. All right, so here are the equations there on the right that I marked that we would code to set the coefficients in the matrix A for this one equation, the first equation for interval I. Okay, now you can translate this directly into MATLAB code. All you need to do is whatever is in a subindex you put into round parentheses, right? And then you set equal to x, I is in a subindex, right? So x of I, parentheses, cubed. That can be translated directly. Let's do the second example, which is equation number 4 for interval I, which was this condition that the second derivative has to be the same at knots. So that's the equation shown here. It is the fourth equation, right, for interval I, so therefore the row number is I minus 1 times 4 plus 4. Okay, what's the coefficient that multiplies AI in this equation? Well, it is 6 times xi. Okay, what's the column number for AI? Well, it's still, as before, I minus 1 times 4 plus 1. Okay, so therefore, if I want to set the entry in the matrix A, it has to be at row number I minus 1 times 4 plus 4. That's the first index. And the column number is I minus 1 times 4 plus 1. And that entry has to be, well, the 6 times xi. All right, next up is bi. What's the coefficient in the equation that multiplies, excuse me, bi? It's 2, right? What's the column number for bi? Well, it's I minus 1 times 4 plus 2. So therefore, if I set in the matrix A, I have to go into the row number I minus 1 times 4 plus 4 and into the column number I minus 1 times 4 plus 2. And the entry there has to be set to the 2. Okay, a little bit more interesting is now this part of the equation, right? It's the coefficient that multiplies A sub I minus 1. It's the A coefficient from the neighboring subinterval. So we're at subinterval I minus 1 with this. Well, first, what's the coefficient for A sub I minus 1? Well, it is negative 6 times x sub I. But what's the column number for this entry? It's not the A of interval I, but it is the A of interval I minus 1. So that just means that if I look at the equation that was for AI and I want to evaluate it at I minus 1, I have to plug into this equation I is equal to I minus 1. So that gives me then I minus 1, which is I minus 2, times 4 plus 1. So that means in the matrix A, my row number is still 4 times I minus 1 plus 4, but now my column number is I minus 2 times 4 plus 1. That's the column that's associated with the a sub I minus 1. And that entry has to be negative 6 times x sub I. On to the last term. The last term is 4 b sub I minus 1. What's the coefficient that multiplies b sub I minus 1? Well, it is negative 2 in this equation. And what's the column number? I'm still at the interval now I minus 1. So the column number has to be I minus 2 times 4 plus 2, right? Plus 2 because I'm looking at the b. So therefore, the matrix A, the row is still I minus 1 times 4 plus 4, but the column number is now I minus 2 times 4 plus 2. And that entry into the matrix has to be negative 2. Okay, good. Now, the right-hand side of this equation. Well, that goes into the vector g, and that right-hand side is 0. Okay, so the entry into the vector g at row number, the row number of this equation, I minus 1 times 4 plus 4, that entry has to be equal to 0. So in that manner, we have built now up the equations and therefore also really the code of how to translate this equation into the matrix entries of the matrix A that we will then have to code. Now in the recitation, we will be looking at the other two equations, equation number 2 and equation number 3 for the interval I, and also the 4 equations for the first interval, so that we will have a complete code in order to calculate all of the coefficients that will define our cubic spline. Now, here is then the general procedure outline of how to do spline interpolation to find these splines f of xk. The first step is to calculate these spline coefficients using the given data. And the way we will do it is we set up the matrix A, the right-hand side vector G, and then we will just call my Gauss-Jordan to solve this system to find all the coefficients A. Then, if we want to interpolate, use these cubic splines to do interpolation, that's what they were constructed for, to the point xk. So we want to find out what is the value of the function at a point xk that is not part of the original data. Then the first thing we have to do is we have to find the interval that contains the point xk, because that defines the cubic polynomial that we will have to use to do the actual interpolation. Once we've found the interval I, we will then just use the coefficients from this interval and plug in the xk value into the cubic polynomial that is defined by ai, bi, ci, di to do the actual interpolation. Thank you for watching.